people sitting down. Well, the first talk is a keynote talk. I don't think I need to introduce Brigitte, but she has been working on many things, and mainly for the mechanization of higher order languages and other things, and today we'll have the type-theoretical form of work for meta programming. And I want to start, but maybe yeah.
Okay, I think the mic is on. So while there's still a seat over there, if you want to squeeze in over there. All right. So what I want to talk to you about is this type-theoretic framework for metaprogramming, and it's something I've been interested in for, 15 years or something like that. And so some of the work I will be presenting was at LIX in 2019, but over the last year, I kind of understood that it's actually a framework for metaprogramming. It's not how we wrote the paper. Okay, so sometimes that happens with research. You learn something later on, how you can rethink some of the work you've done yourself. And so when we started this work, David Thibodeau and Francisco Ferreira, two of my PhD students, were involved in this, together with Andreas Abel. And then now we kind of, this work became has new momentum after the pandemic. And so Antoine Goulin, Jason Hu, and Junyang Jiang, who's actually here, they're involved in this work nowadays. And Jason has by now graduated. So when we think, what I want to do is basically two things. Okay, I want to give you sort of a bit of a background and context in which this work sort of exists and where some of these ideas come from. And then in the second half, I'll explain a bit more how we can turn then these ideas into a type theory. And in the last part, I basically show you some of the new research directions we're performing. So when we think about metaprogramming, many people have different ideas about metaprogramming. Okay, so I think it's good to sort of, that we're all on the same page to define what I mean by metaprogramming. And I think of metaprogramming as a way of writing programs that produce other programs, essentially. Okay? But I don't want to only generate programs. I also want to then manipulate these other programs. So I want to pattern match on the structure of the code I have generated to maybe implement some kind of specific program optimizations or program transformations. Or in the context of a proof assistant, it's basically implementing a proof transformation, okay? Basically like a tactic. And I would like to do this in the same language, okay? So typically metaprogramming systems, and many systems support metaprogramming, they support at least 3 operations and sometimes 4. So the first one is a notion of quotation, where we can quote a piece of code, 3 plus 4, okay? I can think of this as an abstract syntax tree with 2 children, and that is the syntax that I will then manipulate and work with. The second operation is sort of a notion of splicing or code composition. So let's assume code gen of 2 generates this code fragment 2 times 2. And then I can say, well, 3 plus unbox this code fragment, code gen of 2. That will essentially give me this code 3 plus 2 times 2. And these 2 are different abstract syntax trees. Okay? And the third operation that I would like to support is evaluation. So at that point, we want to actually evaluate that piece of code using the runtime system or the evaluation semantics of the metaprogramming environment. And in this case, we do get 7. And the fourth operation that is not supported in all the metaprogramming systems, but it's something I would like to support, is essentially a form of code transformation. So I'd like to be able to implement a program that would inspect the shape of this arithmetic expression, possibly even having some free variables in them in this so it doesn't need to be only numbers, 3 and 4. It could be variables, replace 3 by x and 4 by y. Okay? And I might want to implement some kind of decision procedure for arithmetic. And I would like to simplify this by saying, well, this actually reduces to the left side of this sum expression. And you wouldn't get that necessarily if you have replaced 3 and 4 by variables, Because the way we would normally define evaluation for times, it's recursively defined on the first argument, and plus is recursively defined also on the first argument. So in a dependently typed system, you wouldn't get that equation necessarily for free, but you might want to implement it as a actually transformation of your code. Now, I said metaprogramming is supported widely, and I'm sure many of you have used it. Okay, it goes back to ideas from Lisp and Scheme. We see it in languages like Scala. We see it in languages like template Haskell, MetaML. You see it in some things like MetaCoc. Okay, Lean has metaprogramming. There's something like template Acta. Okay, so it is virtually in every system. And there are good reasons why. Okay, so on the one hand, if you're a programmer's perspective, you would like to implement maybe domain-specific optimizations. So Satnam talked about metaprogramming, for example, in the context of machine learning, where you have a matrix and a vector, and you want to multiply them. And you might want to actually analyze the shape of the matrix, and depending on the shape of the matrix, you might want to actually then generate a more efficient way of multiplying the elements of the matrix with your vector. In particular, if it's sparse, and you have an entry that is 0, you might not want to generate 0 times this element from the vector. You might want to just throw that away. There's also, certainly, it supports macros and boilerplate code. Okay? And in proof environments, there's this idea that we want to use reflection. So you basically quote a proof goal. You get the syntactic representation of your goal. You can write a transformation of that goal. Okay? So by, for example, calling a tactic or a decision procedure that will transform it into something else. And then you reflect it back to the actual proof assistant you're working with. But there's sort of something unsatisfying about this from my point of view. Okay, so first of all, I personally believe in types. Types are good. I think many of you believe types are good, hopefully. So, because types allow us to read out errors early on. They give us sort of a good safety net for the things we work with. Okay. But if we look at how metaprogramming is realized in languages like template Haskell or MetaCoc or Lean, it is really you get an untyped representation of the code. Okay. So there's certainly work on typed template Haskell. But if you look in proof environments like Lean or MetaCoc or template Acta, what you get is essentially a data type that's called TM, and it codes up all the terms in the calculus of construction or all the terms in Martin-Loef type theory. And then the first question is, how do I represent variables? Well, variables are just De Bruijn indices. They're not even well-scoped De Bruijn indices. Okay, so you can do all kinds of De Bruijn index manipulations, just the same way you can do pointer arithmetic. You can now do De Bruijn index manipulations. Okay, and we believe pointer arithmetic is bad, and I also believe managing your De Bruijn indices explicitly is also bad. Okay, so why do we not use something better? Okay. And in particular, why don't we use something that actually guarantees that the objects we're having are well-typed objects? Okay. And MetaML certainly took the lead on this, early around 2000, to actually support a form of typed code generation. Because if it is not typed, right, then it's really hard to test and reason about the code generation and the generated code itself. And you will catch errors not at the generation time, but essentially when you're using it or when you're running it or using it in some form. And the last point is also very close to my heart, and that is sort of more a philosophical objection I have to these systems. Because what happens in these systems here, like MetaCoc or Lean, it's essentially clever engineers added to the system a way of quoting. And that's great. I have a lot of admiration for the people who did this. Okay. But what I would like to know is, what is the type theory we are now working with? Okay. It's certainly not Martin-Loef type theory. It's not the calculus of construction, because it's Martin-Loef type theory plus this quotation thing. Okay. And so what is it? Okay. So since I'm a theoretician, I'd like to understand what it is. And so really, I would like to understand what is the type theory behind quote, unquote, eval, and pattern matching on code. So what I want to tell you about, I want to take you on this journey, essentially, of developing these ideas that go into this type-theoretic foundation for metaprogramming that would allow us to catch errors at the time we're generating code. We can also then reason about the code generation and the generated code, because we're working in a type theory. Okay, so we can prove properties about it. We want to have a support for code analysis, so pattern matching on code, so we can write our own tactics within this language. We'd like to have a proper logical foundation. And the last point is something I also think a lot about, because if you think about writing a decision procedure for propositional logic, okay, or for Pressburger arithmetic, that's not, you don't need to handle all of Martin-Loef type theory, right? It's a fragment of it. And in some sense, I know what fragment I want to handle. Okay, I want to handle propositional logic. Okay, I want to handle Pressburger arithmetic. So really, what I would like to do, I would like to write metaprograms over sublanguages that you can carve out and then make statements about. So, so let's start at the beginning, okay? Because I don't make any assumptions that you know anything about type theory. Okay, so where should one start? Okay, and so in fact, there was a very beautiful observation back around 2000 by Rowan Davis and Frank Fenning, who observed that the box modality from the modal logic S4, which is the necessity modality, can be used to describe closed pieces of code. Okay? And the reason is because if you say A is necessarily true, it is something that is really true in every world, okay? And that means in every stage, and so you can basically run it at every given stage of your program. And that gave you the separation between generating code, okay, which was essentially of some type B or C, and then the code that was being generated, that was essentially of type box A. But this work is only simple types, right? It doesn't have any pattern matching on code, okay? So that's still a long way from what I actually want. But there was certainly work in between, okay? So around 2008, for example, we extended this idea to the idea that we can describe open code, okay? So that means code of type A that has free variables in it, and these free variables are in gamma. And at POPL in 2008, in fact, I proposed a language that did support a form of pattern matching on these kinds of contextual objects, but it was mostly simple types, okay? And it was the basis of this programming environment, Beluga, that some of you might have heard of. And ultimately, this led to this paper in 2019, which is actually a Martin-Loef type theory that allows you to talk about open pieces of code and allows you to pattern match on these pieces of code. So we'll start slow, okay? We'll start from these ideas and we'll end up in these ideas, okay? So no worries. So what's the general idea? So let's look at some examples, okay? So there's no talk on metaprogramming that can live without the power function. So here we have a natural number, and it generates code, namely a natural number that depends on this variable x. And if you have power of 0, then you return 1. Okay? It raises x to the power of 0, which is 1. And if you have power of n, you compute power of n minus 1. Okay? So that will compute already n minus 1 times x, okay? X's. And then you compose this code and multiply it by x. Okay? So if you have a power of 2, a power of 1 will generate 1 times x. Okay? And then you splice that in with this additional times x. Now, you might say, well, okay, but how do I know, okay, that power of 1 actually generated 1 times x, okay? And this is this x that I want to have, and I'm generating power of 2, because in some sense it should, the name shouldn't matter. If I use it x, y, or a or b, it should be the same. And so really I was lying a little bit here, okay? What we should have here is an unbox or a splice that will possibly rename the free variables in this open piece of code. Now, renaming is maybe not that interesting, but what is more interesting is if I actually refine the piece of code, okay, or specialize it. So here's a program where I want to get the nth element out of a vector or a list. I restricted it to natural numbers lists. And if you get the 0th element, it's the head of that array, of that vector, okay, or that list. And if you want to then compute the nth n element, okay, you compute nth of n minus 1, okay, and then you need to replace that list with the tail of that new list, okay. So you see that actually happening here. I mean, nth of 0 will compute the head of x. When I want to get the first element, then, okay, I need to take the tail of the head, Okay? And if I have nth of 2, I do head of tail of x. Okay? I have 2 tails. So if I have here nth of 0, okay, I'm going to replace this x with tail of v, or tail of x. Okay? So I get this tail thing in it. So I can specialize head of x to head of tail of x. Okay. So here we see that it's not just doing a renaming. It's actually doing a specialization of the code that we've generated prior. So what's the theory behind this? Okay, so there are typically sort of 2 different strands of theory that could support this form of a box modality. And I'm going to show you one that is really focused on this box-unbox idea, which is really grounded in sort of this, in this model-theoretic view of modal logic, where you have this notion of Kripke worlds. Okay, now this is maybe a funky words you don't know much about, so that's okay, because we are only restricting this to 2 stages. Okay, so what I will do is I will take the original work by Rowan and Frank, restrict it to 2 stages, and I will make it more general by looking at how we can make it contextual. So if you, and for pedagogical purposes, I'm going to disentangle these 2 stages. Okay, so you have one stage which describes the code. In our case, simply type lambda calculus. Okay, so that's in blue, and it has variables, functions, applications, and we know exactly what types we have: natural numbers and functions. And then we have a level where we have programs, and that's where we extend, in some sense, our simply type lambda calculus with the ability to quote code. Okay, so here we quote code, quote that it stands for a simply typed expression. And we have a way of describing the type of that piece of code. It's of type tau with a context gamma. And the splice, so which was previously written as unbox, okay, I wrote it here with these angle brackets. Essentially, here we splice in a program. We would evaluate this program to a piece of code, to a piece of syntax. And then the sigma is this width, okay, where we do some renaming or we replace the variable with a tail of some other variable, okay, so which basically gives us this refinement. And then we have here eval, which takes in a meta program, it evaluates it to some piece of code, and then we use this runtime, this environment row to actually run it. Okay. So you see that there's already a lot of overlap with the syntax, but really it's useful to sort of separate them, especially if you want to do pattern matching, because here I actually know exactly the shape of the code, right? If it's a fully evaluated piece of code, a full value, then it will be exactly describing the syntax of the simply typed lambda calculus. And essentially, you have 2 levels of typing. One that is the level for typing program expressions, and one is the level of typing for code that can refer to the local variables, which are in gamma 0. These are code variables. And gamma are still program variables that might be used, because I'm referring to programs, right, by unboxing that variable or unboxing nth of n minus 1. N would be this kind of program variable. So what does this look like? Okay, well, everybody hopefully is in some way vaguely familiar with the simply typed lambda calculus. So this is the simply typed lambda calculus. Okay, everybody happy? Now this is also the simply typed lambda calculus. Okay. Except that I have 2 contexts. Okay, I have the context that says I have here the local variables that describe code, and these are my program variables that I could still access. And how do I access program variables? Well, I haven't shown you box and splice. So I access program variables because I can essentially refer to programs. Okay, so that brings me back to the previous world I was in. And that will denote a piece of code. And then I have here a map that moves me from gamma 1, which are the code variables in the code that I've generated. And I want to use this in a code context where I have gamma 0, so I need a substitution or a map from code variables to code variables.
My poor eyesight doesn't let me.
Yeah, this is.
Box.
Sorry, I can't change that. So this is just says gamma and gamma 0. Okay, and this is referring to the turnstile, which is for the code typing. This is sigma, which is a substitution, and this is gamma 1. Okay, so gamma 1 comes from here. Gamma 0 comes from here, so it's a transition between gamma 1 to gamma 0. That's what it means. Okay. And in the introduction rule, it basically says when is a piece of code well typed? Well, we transition to type checking E as code. Okay. So we go back between these two layers. And for the elimination rule, which is actually logically on box 0, okay, it is this law that basically says if you have box A implies A, then we, again, evaluate E to a piece of code. And then this here is a transition between gamma 0 and these program variables. Okay? So this is a bit different because it means essentially you have code variables for which you plug in actual program variables, program values.
What's the hat on the gamma 0?
So the hat here is essentially saying it's only a list of variables without their typing annotations. Just the same way I don't have typing annotations on the functions, I didn't want to have typing annotations on the variables that can appear in the code. Okay? Yeah?
Does that mean that these are still untyped syntax?
This is typed syntax because I have a piece of code, E, that is of type tau. And this gamma 0 will tell me what the type of the variables are that are free in E, because I'm checking E with respect to gamma 0. This is, so this is fully typed. Okay. Good questions. Thanks. Feel free to interrupt. Okay. Okay. So I want to highlight sort of this difference, right, between a map. Here, sigma is a map between code and code. Over there, if you want to really run it, you have to instantiate code variables with some programs or some program values. So, I mean, you see this is, of course, verbose, okay? So that you can now see why Frank and Rowan sort of collapsed this into one system, okay, where you write essentially on the left side of your turnstile a context stack that models n possible stages you have, okay? And then you don't have to duplicate these rules. But the advantage of a presentation like this is really that it gives you a clear idea, right, what is at the bottom stage, okay, at the lowest stage. It is really the syntax of the simply typed lambda calculus. So, so we're going essentially between these two worlds, right, the world that is code and the world that is programs, and we go between them using box and unbox. I restricted it to 2 stages, so there's nothing like box A. The code is a sub-language of our language of programs, and that's in some sense exactly how quotation is handled in proof assistance, where when you say quote in Rock or in Lean, you get essentially a data type that does not contain quote itself. Okay? It's a pure calculus of construction term. And so knowing what the sublanguage is actually really important for pattern matching, because if I now say I have a piece of code that describes a natural number, I know exactly what shape it is. It's either a variable, it's a function, or it's an application. Okay? It cannot be some complicated program that uses some kind of box thing. Okay? That's just not allowed. So how do we get to a type theory? Okay? So we use the same idea of 2 layers. Okay? We have a layer of metaprogramming. Okay? That's not simply typed anymore. Okay? It's actually Martin-Loef type theory, so it has a universe hierarchy and all the things you want. Okay? So type level computation, but it's essentially replacing this outer layer with Martin-Loef type theory. What's the level of code? Well, on the level of code, I am going to actually use something called the logical framework LF, okay, which is a slight detour. I'm not representing Martin-Loef type theory itself or the simply typed lambda calculus itself. I'm representing a framework which allows me to encode these different languages. But the idea will be that I go between these levels, okay, with box and unbox. And if you want to take a sort of a slightly different view, it means you have a dependently typed metaprogramming language. That is Martin-Loef type theory. We have box there. Okay, we have pattern matching on code there. And what is inside the box is coming from the logical framework LF that allows us to represent abstract syntax terms with something called higher abstract syntax, which I'll explain in a minute. And we're encoding these different sublanguages in LF. Okay, so in particular, what I want to do, I want to encode the simply type lambda characters in LF because that's the language of code that we had previously. Okay. But I can encode in here also system F, and I could encode in here the characters of construction. And if I want, I can encode session type processes. I can encode propositional logic. I can encode Pressburg arithmetic. Okay, we know that the logical framework LF is very flexible in what it allows us to encode. And that means I get a meta-programming system on the simply type lambda calculus, a meta-programming system on system F, a meta-programming system on the calculus of construction. Okay. So what is LF? Okay. So LF is an idea that was proposed in the 1980s by Harper, Hansel, and Plotkin. And then Frank and Connell Elliott coined this term higher order abstract syntax. But essentially, it's a language that is the dependently type lambda calculus that will serve as a language for representing formal systems. And the idea is that we will model, we will use the function space that exists in here to model binding in our concrete object language. So let me show you. So we had the simply type lambda calculus. Okay, we had nat and tau1, arrow tau2, and we had terms, acts, functions, and applications. So I'm going to define two types, TP and TM. And here I have nat and arrow as constants. And then I define two constants, fn and app, corresponding to this guy and this guy. And the interesting part is now that fn takes in a function from tm to tm. Okay? So I'm not modeling variables via de Bruijn indices. I'm modeling variables by piggybacking on the notion of variable that already exists in LF. So if I want to model nat to nat, then this is arrow nat nat. That's how we would encode it. If you have the identity function, then we encode this as the constructor fn. And then here, this Greek orange lambda is the LF abstraction. And then it returns x. So I immediately get here alpha renaming, just the same way I get alpha renaming in here. I get overshadowing. Okay, so although I wrote here x, an orange x and a blue x, I just use different kinds of lambda abstractions. And here is fun x, fun f, f applied to x. I get lambda x, fn, lambda f, app, fx. So the slogan is you model variables from whatever object language we have here, the simply type lambda calculus from before, by variables in LF itself. And we inherit sort of this notion of alpha renaming from LF, because we know how to do alpha renaming for these Greek lambda functions. Okay, we know also how to use these lambda functions, right? So I can apply this lambda function with another term, and I will substitute for x that term. So I can do this for typed representations, okay, by indexing essentially tm with tp, and I'm representing fn as a function from tma to tmb that will then produce a term of arrow ab. And here you see the notion of terms actually didn't change, and that's because I omitted all the implicit arguments that refer to the types of these terms or subterms, and that can be inferred. So the bottom line is, okay, if you now have LF, which is a dependently type lambda calculus, you can represent syntax trees with binders. So Dale Miller likes to call them lambda trees, for example. Okay. And this works because these LF functions purely encode variable scope. They don't encode recursion or pattern matching or inductive types. Okay, it's a very weak calculus. And the benefit is you're basically implementing all the binding infrastructure once and for all, and then you're sort of leveraging that. Okay. And this scales to encoding systems like system F or the calculus construction, or even to represent typing derivations. So now we want to write programs about these structures, right? I said I want to do pattern matching on these structures, and so the simplest program I could imagine is computing the size of such a term. And now I need to pattern match on this term. So I will pattern match on the substructure, and x becomes free, and then f becomes free. And so I have these red variables that are basically free variables. And so that would mean, well, pattern matching doesn't fully work. Okay. And the answer here is essentially contextual types come to the rescue. Okay, so if you want to think about how do I characterize what is inside this box, it's useful to think about how I would type such an expression. And we type this expression in a context where we have x. So we have x, which is a term, we have fn, and then we have the rest of this expression, and the whole thing is a tm. And if I want to know what is inside this box, well, it will be a tm that depends on x and f. And so the idea is that we're reifying this typing judgment, right, which is here written with these 2 bars, as an actual proposition or an actual type. So we do this actually quite often in logic, right? So if you think about the implications, implications are the syntax for expressing that something is hypothetically true. Okay? So we might have a hypothetical derivation, but in order to talk about that on the propositional level, we actually use the implication sign. Okay? And if you have a parametric derivation, if you say, this is something that you've proven for a particular parameter, you want to express that as on the level of propositions, you use a universal quantifier. So here is sort of the same idea. Okay? You have a typing derivation, and you want to talk about that typing derivation on the level of types or propositions, and we reify it as syntax. So contextual types reify these typing derivations. Okay? So now I can write this program size. Okay? I can start out in the empty context, and then as I go, I will add these variables to the left side, and everything remains well scoped, and everything remains well typed, if you like. Okay? So in order to give the type to size, we would need to say, for all contexts, if you give me a term in the context gamma, then I will return an integer. And when you want a pattern match, you know exactly what you're pattern matching on. It's going to be an fn, an app, or it's going to be one of these variables that come from your list of variables over here. And for that, we have a special pattern variable. And while I simplified this here to work on an untyped representation of syntax, you can do this on typed representations of syntax. Okay? And pattern matching then is basically pattern matching on higher order patterns. That's also a decidable fragment, and so we trade off essentially ML-style pattern matching to higher order pattern matching. So the general lesson, if you want to model code not with the Brin indices, you should model code with higher up syntax trees, and in particular, you should pair these trees together with the context they live in, and then you can essentially model pattern variables again as these contextual meta variables, and you use as pattern matching higher order pattern matching. So, how does this type theory then look like? Okay. So as I said, okay, we have here the meta-programming language that is a Martin-Loef type theory. We'll have a quote, and it will have an iterator over pieces of code. And just as before, we're checking this piece of code by checking M to be a well-formed piece of code. So we're transitioning to the LF level. And on the LF level, T will be a program that could generate a piece of code. So T is a program that generates a piece of code of type A in phi. And we can refine it by applying sigma. Okay? And since we're working in a dependent type theory, A might depend on phi, so we need to apply sigma to A. So now our type theory rules are intertwined, and also our equational theory and our weak-head reductions are intertwined. Okay? So the main challenge then is, how do we actually prove normalization? Okay? And that's what our paper at LIX actually did. Now, another question you might say is, well, can I now embed, right, the language I've given you in the first part of the talk in this framework? And the answer is yes. Okay. If I would, for example, what kind of code did I have? Well, it was a simply type lambda calculus, so I define an embedding. I map this blue fn to my constructor fn, my application to this constructor app. Variables are mapped to variables. And if I have here a program expression, I need to translate my program expression. Okay. And how do I translate programs? Well, E is already a subset in some sense, of what I have in Martin-Loef type theory, because these are simply type programs. So if I come to a boxed piece of code, I need to translate it and map it into my encoding in LF. But the main question is what happens to eval? Okay, and I haven't really talked about eval at all. And the reason is because this Martin-Loef type theory does not have eval. Okay? It doesn't make sense to define a generic eval for this logical framework LF. We can only define eval for specific sublanguages. Okay? But we have pattern matching, okay? And we have what is called large elimination, so computation on types. And that means actually we can implement eval as part of our type theory itself. So we don't need to add it to our type theory because we can define it. Okay? And the idea is that we define essentially a function reflect that would take in one of these syntactic representations, so for example a nat, and it would reflect it to the type that we have in our Martin-Loef type theory, namely nat. And if you have arrow ts, then you reflect t. This is the arrow from our Martin-Loef type theory, and you reflect s. And the eval function will pattern match on these terms that have a type A, and they live in a particular context gamma, and we're going to reflect them to terms of type A, okay? Of reflect A. So if A is nat, this part here is a term of type nat, and we're going to return an object that is of type nat, okay? Now the main thing that we still then need is what happens to these variables in gamma, okay? And that is essentially a function that will map the LF variables. Okay, so this is one of these LF variables. These LF variables that are of type B to values of their corresponding type. So if B is a nat, a TM nat, it will reflect it to some value in Martin-Loef type theory that is type nat. Okay. So that means we can actually adequately represent, in this case, lambda box in Cocon. Okay. And so now you have a framework where you, of course, can not only represent simply type lambda characters, but you could say, well, I'm going to represent system F. Now, for system F, you can't write such an eval function, okay, because system F is actually not a sublanguage of Martin-Loef type theory. Okay, it has impredicativity, and Martin-Loef type theory doesn't. Okay, so you cannot write an eval function for all languages. Okay, but for some, you certainly can, right? So we proved normalization and consistency of Cocon using sort of a standard method of logical relations. So if you're interested in that, you can read that paper. We have given a category theoretic foundation for this together with Jason and Ulrich Schirp. And it turns out that Cocon is actually the syntax of a paper that has been written probably also 15 years ago by Martin Hoffmann, who gave a semantical analysis of this higher obstacle syntax idea. But there was never really a type theory to sort of express it properly. And in fact, Cocon is that type theory. Okay. Now, the next step we might ask is, well, can I use this? Okay. This is in any form available. Can I implement this? Okay. And so at the moment, this is not implemented. So then the question is, how would I implement it? And there's sort of a choice, right? Normally, like how we implemented Beluga or how Agda is built, right? You look at your type theory, you've proven your properties, and then you choose your favorite programming language, right? In Agda, they choose Haskell. In my case, we chose Beluga, and then you define a data type in OCaml that represents this, and you implement your typing rules, and you make certain optimizations to make this work. Maybe you use more an explicit substitution calculus that deviates already a little bit from your theory, okay? But it's sort of unsatisfying, right? Because as you start implementing, the implementation will deviate more and more and more from your actual theory. And in fact, that's the reason why Beta-Coq was created. We wanted to narrow that gap, right, between the theory and what was actually implemented. So we took a very different step here. Okay, we basically decided that we would build a correct by construction type checking kernel, and we started with Martin-Loef type theory and Cocon. So we described declarative typing and declaratively this normalization by evaluation algorithm, so a slightly different proof technique. We mechanize this typing and algorithm in Rock. We implement also, we prove properties about this normalization algorithm. We prove it, for example, to be normalizing. We implemented an algorithmic typing and functional NBE. In fact, a lot of credit goes to Claire here. And then we extract from it a core kernel, a type checking kernel to a camel. And then you can use this as a trusted backend. Okay? And the goal here of this work is both to extend it to Cocon, as well as to provide a trusted backend to other type checking systems, such as Martin-Loef type theory, or other type theories, okay, that we want to then explore. So it's also meant as a kernel for exploring different mechanizations of type theories. And if you're interested in that, you can talk to Claire, and we also have a talk on Saturday. Now, we also looked at other extensions of this meta-theoretic framework. So in particular, we looked at how to do meta-programming on System F. So that is also work Claire has been involved in. That was at POPL in 2022. And it does support pattern matching on polymorphic code. It supports nested boxes, but there's no normalization proof. Okay? But it does represent essentially code in this Hoa style, okay? Without the embedding, but more directly. And then very, very recently, so Jason is a PhD student of mine who has graduated just in November. And here we have developed a Martin-Loef type theory that has also layers, but it actually has really directly you pattern match on Martin-Loef code. So there's no notion of encoding Martin-Loef type theory in LF or anything like that. You basically have Martin-Loef is your syntax, and Martin-Loef extended with box is your meta-programming language. Okay. And the advantage of this is that we can also pattern match on it, but in particular, you get different equations on the code, or on the type of the code, or on the meta-programming setting. And so we've proven, in fact, that the system is normalizing. And this work here is sort of extending this original work by Frank and Rowan. That was a Kripke-style modal type theory, unrestricted, n stages, okay, and built an intuitionistic type theory around it. But here we don't do pattern matching. Okay. And the other two projects I want to mention is essentially research that we are doing in generating code that represents session type processes. Okay. Then you have two completely different languages. You have one that is your meta-programming language, and the box, the code that you're describing are essentially processes. And then sort of even further, if you want to talk about different layers of sub-languages, okay, we've been proposing a system that uses not box, but uses something called an adjoint modality. And that gives you sort of a very flexible way of connecting different languages. And it moves this framework almost to an infrastructure for interoperability. So there are a couple of lessons, I think I've learned along the way. One is that I do think contextual higher order syntax is a good way of representing code. There's no reason we need to expose to programmers the underneath gory details how we're representing variables. Okay. We like higher level languages, but we don't work with low level representations, right? Why should we expose it when we work with code? Syntactic structure of code. Layers give us a way of syntactically characterizing the code and distinguishing it from the meta-program. And moreover, these layers actually allow us to control operational behaviors and equivalences. Okay, so we might have different equivalences on the code versus the program. For example, 3 + 4, if it was a part of your code, it did not reduce. It was on the level of program, you do reduce. Okay? And pattern matching gives you the ability to actually evaluate code. So if you have the ability to have pattern matching and you have a rich enough type theory, you don't need eval in your metaprogramming system. You can define it. Okay? And Cocon is sort of a language that prioritizes sort of the representation of different languages, that then kind of interoperate. Okay, so that's a design decision you make at some point along the way. All right. Well, thank you. I'm happy to take some questions. Yeah.
Thank you. I like to talk. I'm very interested in metaprogramming, and one of my favorite examples to figure out how to type check, it comes from Racket, where a lot of Racket code manipulates binding. It's not merely lexical binding, but you may export things. But my favorite example is struct in Racket, which generates several bindings using basically an algebra on identifiers. And I have no way in Racket to predict and say like what I expect such a macro to do, like how it will manipulate binding, what names it will export, and how are they calculated. And I'm wondering if you've thought at all about this problem. Like, how do I not only say I expect something to be in scope, but I expect several identifiers to be created following a certain pattern?
Yeah, so I think if you have large eliminations, you can more talk about the different types you're actually creating. So there's on the template Haskell website, there are similar problems, and they work very well on the untyped setting. And the question is, how do you do that in a typed setting, right? And essentially, it's a slightly different problem, but I think it's similar. Okay, so what they wanted to define is sort of generate code or functions that have n input arguments. Okay, depending on the first number. So I want to generate a function that, and maybe even paired them. Okay, so I have a pair, I have one argument, I have a pair of 2, a pair of 3, a pair of 5, and so on. Okay. And that is not necessarily easily typed in a simply type language, right? So for that, you need a richer type system if you wanted to express that.
Okay, thanks.
Yeah, thank you very much for the great talk. Really appreciated it. So you're using higher order abstract syntax to represent the binding of the meta language, right?
Okay, LF is my meta language in this case, and then it's the binding of my object.
Yeah, because it gets kind of confusing.
Right, so let's say if I have OCaml, I would represent the bindings of OCaml with bindings in LF, yeah.
So, but anyway, so my question is, so there's also like this lesser known idea floating around for a few years, instead of using de Bruijn indices, using co-de Bruijn indices.
Right.
I don't know whether you're familiar with
that.
Yes. Do you know whether it would be would also fit in your framework using co-de Bruijn indices, or is it like even worse than pointer index arithmetic?
I've been on record saying, and I'm saying this again, that I passionately hate de Bruijn indices. Okay, although I have been using them, of course, in all our implementations, and co-de Bruijn indices, in my mind, are even worse. Okay, okay. Because I mean, they were originally, I think, proposed in the setting where you have substructural systems, right, where you need to separate your context, and then it becomes sort of not meaningful anymore what its reference is. And so when you think about a linear type system at the axiom level, when you look up a variable, there's only one assumption. So of course, the number of this variable needs to be 0, right? And so what happens now if you look at the representation of your term, all variables will be 0. Okay, because they're always typed in a context where you only have one variable, so the index will be 0. So reading a co-de Bruijn term is even worse than reading a normal de Bruijn term, okay, in my mind. But
okay, quick. I was wondering if there are any applications also to data type generic programming of this approach.
In what example, or what do you have in mind there?
Like basically having some products or something like that for data type and generating functions based on that.
So I guess the best case I can say is in this work, in the first work here in Mint, we give several examples of how we would work with sums of products like that, if n-ary sums, for example, and how to do metaprogramming for that. So these are some of the examples we've been using, and you really require the full power of dependent types to express the typing invariances for it.
Thanks. Okay, thank you.